Yes, thank you very much. And thank you all for giving me the opportunity indeed to tell something more about the digitalization of formulation R&D via science-based web apps. You can all see my screen properly?
Yes, we can. Thank you.
Okay, cool. Right, indeed. So my name is van Loon. I'm the founder of Van Loon Chemical Innovations, VLCI, and we are a small group of formulation enthusiasts and striving to accelerate your chemistry. We do that by the practical implementation of predictive formulation sciences, HSP and HLD, which I will explain further in this presentation. And we combine that with high throughput screening. I will also tell you why we need high throughput screening in order to make science-based formulation happen in the industry. So we work for companies all over the world in the field of personal home care, coatings, polymers, agrochemicals, well, everything that has to deal with formulation developments. And nowadays, we are also selling licenses on our web apps, which will be further explained in these presentations, including some practical examples. I see already a lot of presentations with a lot of modeling and a lot of equations and data. I think this presentation is a bit more practical than that, and I hope you will like it. So, why are we so much focusing on HSP and HLD as a formulation science to implement for formulation developments? Well, that is because HSP is applicable to solutions and dispersions, so not only to solubility, as the name suggests. So we are changing the name actually to Hansen similarity parameters, and I will explain you a little bit more about that. It's a very effective matchmaking systems in order to give a practical parameter to ingredients in order to formulate solutions dispersions, but also to some extent, when it comes to compatibility between surfactants and oils, you can also apply it to emulsions. But if you really want to develop specific emulsions, like water in oil, etc., then the HLD, the hydrophilic lipophilic difference, does not the balance, but the difference makes a lot of difference, is there to give practical parameters to surfactants and oils, and based upon the equations, you can then formulate your specific emulsions. And both those sciences we also apply as a service in our company in order to determine them for ingredient suppliers, for example, but also to implement them for formulators. So using those two formulation sciences, you can actually develop any type of product, a solution, a dispersion, and an emulsion. So it doesn't matter what kind of product, like a personal care, home care, coatings, etc. Every type of product can be developed via those sciences. And because they work from the inside out, from the ingredient parameter, you can match ingredients together. And because of the thermodynamic equations, they like each other when they are matched. So it's a matchmaking system, actually. We also make it online. It's almost like a dating app. But when doing so, everything performs to the utmost. That means you can improve your properties. And I already saw now the presentation about efficacy, for example. You can also improve the efficacy of your formulation by using HSP, for example. So there will be an example later on in this also. We're also talking about rheology in the beginning of this Congress. This can also be tuned by applying HSP or HLD. So there are a lot of opportunities to improve your end properties of formulations by applying those sciences. So Hansen similarity parameters, how does that work? It is a sustainable, predictive ingredient parameter in order to develop solutions, dispersions, and to complement emulsions, as I mentioned. It consists of three parameters: the delta D for dispersion, the delta P for polarity, and the delta H for hydrogen bonding. So three parameters. And you can obtain those parameters for all kinds of ingredients out there used in formulations. So polymers, oils, solvents, pigments. Yes, there's also things that doesn't dissolve. There are two ways in order to get to an HSP. You can calculate it based upon the smiles of an ingredient, but it's rather difficult for polymers or complex structures. So the correlation between the practical use is a little bit less than when you do the experimental HSP determination. And that is how we normally determine HSP. So we have a set of solvents of which we know the HSP of. We add an unknown ingredient to it. We give them to rate all those solvent samples. We enter it in the software from Hansen, the HSP IP, and then we generate the center coordinate plus the sphere. So if you calculate values, you only get the center point. But if you do it experimentally, you will get the center plus the sphere. And the sphere says something about the range of compatibility of your ingredient, actually. So that is your like region. And if other ingredients are inside that bubble, that sphere, then they like each other. That means they form something stable. Yeah. The beauty of HSP is that it can be sustainably used because it is a fixed parameter. So every ingredient has its unique center coordinate and radius. Yeah. So matching ingredients is now possible because if another center of an ingredient is inside the sphere of another, then they like each other. So therefore, you can develop complex formulations with HSP by mapping all those spheres into Hansen space. So there are equations for it to measure the distance, the center-to-center distance, and if they are inside the radius. So that means that the center-to-center distance is divided over the radius. So if the RAD is below 1, it is inside the sphere. So the blue dots in this picture. And if it's above 1, it is a red dot. That means it's less compatible. If it's too far away, it is not compatible at all. So here are the ones that are very good inside the sphere, and then less and less and less, or even non-compatible ingredients. Sometimes you also want to know to which ingredients your packaging material, for example, is non-compatible. So to make sure that that doesn't leak through your packaging material. So this is how you can formulate with HSP, by using those equations, the distance equations, in order to find other ingredients for your formulation. Then HLD, hydrophilic, lipophilic difference, only applicable for emulsions, to develop specific emulsions. Again, it is a predictive ingredient parameter, in this case for oils and surfactants, and also can be used in a sustainable manner. So this is the equation. The HLD equation takes into account the salinity, either the external salt that you add, or that comes from a ionic surfactant, for example. Then the EACN, the effective equivalent alkane carbon number. That means how oily your material is. It's applicable to oils, mineral oils, vegetable oils, but also for monomers and polymers, etc., etc. The higher the number, the more hydrophobic a material is. You can also blend ingredients together and calculate the blend EACN. Then the temperature, the deviation from 25 degrees, and the CC is the characteristic curvature of a surfactant, applicable to all kinds of surfactants: synthetic, bio-based, ionic, non-ionic, etc., etc. And again, you can make blends of ingredients in order to get to a certain CC. The higher the number, the more hydrophobic a surfactant is, the more it likes to be in the oil. Then you have FA, which is used for all the other additives like fragrance or preservatives, etc. They also have an influence on the balance of your emulsion. So then the HLD is your equation or your guidance in order to develop specific emulsions. HLD 0 is the microemulsion region. That's where everything is happy together. Like the HSP, where everything is thermodynamic stable. That means it doesn't really form an emulsion, but it's more like a dancing solution, let's say, where you can find the lowest viscosity, for example, but the highest stability of your formulation. You know? So that is normally how we determine ESEN or CC values of unknown ingredients, because when we fill in 0 in the equation, we know, and we have a scan of which we know all the ingredients, and then we add one unknown to it, one unknown oil or one unknown surfactant. And based upon the blending rules, we can calculate back what the CC or the ESEN of the unknown ingredient is. Once you have it, then, so if you have your ESEN blend, your salinity, temperature, you can then calculate which CC do you need in order to get to a certain HLD 0 point in order to select your surfactants. Again, you can make a mixture of surfactants in order to get to the required CC. I will give you some examples. HLD below 0 gives you the oil and water emulsion, and the best region for this oil and water, the classic emulsion, let's say, is around -1, where you have the smallest droplet size and the best stability. On the other end, HLD above 0 gives you the water in oil. Again, around +1, you will get the smallest droplet size and the best stability of your emulsion. Yeah. So whatever you fill in for HLD, you can always calculate which CC do you need in order to develop that specific emulsion. So, and again, you can then find your best surfactants, blend them together in order to make the emulsion of your ESEN oil, a monomer, polymer, whatever you want to emulsify. So with both, you can predict compatibility and improve performance and better understand the interactions between ingredients. You can reduce complexity because you can streamline the number of ingredients, so using less materials, ingredients in your formulation and their concentration. You can also do replacement of ingredients. Once you know the area of HSP or HLD, you can find alternatives with same parameters. Yeah? So then you can easily switch to bio-based solvents, for example, or bio-based surfactants, etc. You can also make specific ingredients compatible. If you have ingredients that doesn't overlap or doesn't match, you can find something in the middle in order to bridge those ingredients to make them compatible in your system. You can tune blends. For HSP, you can tune blends of solvents in order to get to a certain HSP value. And for HLD, we can then tune blends of ESEN or CCs in order to get to a required parameter. But most of all, it is sustainable data. Once you have the HSP and HLD of your ingredients, it's fixed. And that's why we are using this in order to digitalize R&D. And that is how we differentiate from all the other digitalization approaches, where you always need experimental input in order to build your models. And here it doesn't. You use HSP and HLD in order to select your ingredients, etc. But there's a small problem because science-based formulation is quite hard and people find it difficult to understand. And there are so many ingredients out there and not so many HSP and HLD of commercial ingredients. It is very time-consuming and it's an error-sensitive task. So if you have 10,000 of ingredients out there, it will take years. So people always see the big mountain like, oh my God, I'm not going to do that because, yeah, you know, we have to make a lot of samples, we have to characterize them and blah, blah, blah. So the solution is simplify it. and make it accessible. And we do that via automation and web apps. So preparing those samples in order to determine HSPs and HLD, as I said, with a set of scans that we know the parameters of in order to get the unknown. We do that already via our Formax, that is a high throughput system from ChemSpeed, where we can prepare all those samples and also the formulations. But we still have to characterize all those samples because we make hundreds of samples. So while we make, let's say, 50 samples per ingredient in order to get an HSP or an HLD point. So you can imagine how many samples that we need. We developed formulation apps using a central database. And I will explain you more about that. But in order to get the sample evaluation done right and more accurate, we are building robots in order to screen those samples that we prepare. So then we can finally screen a lot of samples and get their HSP and HLD, because we're using picture analysis in order to screen all those samples that we prepared and say, okay, this is an emulsion, blah, blah, blah. Here's your HLD 0 point, so we can determine the ESCN or CC values. Or these and these solvents are good solvents. So that means here is your HSP point of the unknown. So that is how we catalyze actually the implementation of science-based formulations, HSP and HLD. So we have created the world's largest central HSP and HLD database. We call that PredictID, Predictive Ingredient Database, where we include our own, of course, non-confidential data from commercial ingredients. And we also working together, as you can see here, with suppliers in order to get their ingredients in this database as well. And they can even link that to their own digital tools. If they don't have it, they will get a bunch of HSP or HLD for free, because we want to build this database further. And most of all, our users can guide us on which ingredients they want in the database. And that is actually good, because now more and more ingredient suppliers are aware of the use of HSP and HLD, that our formulators are in a need in order to have those values available in a database so that they can start formulating. So with this database, we connect that to our web apps. We call the HSP web app PrediMatch. It's here on the left side. And PrediMulsion is our HLD-based web app here on the right side. So with those apps, you can see that all those ingredients are now data points in the app. And you can narrow down formulation space a 10-fold in order to develop your coatings, inks, personal and home care products. Yeah. So people are using the central database, of course, in private, but everyone can use this data in order to develop their products, to select and visualize their ingredients, find matching ingredients, compatibilizing ingredients, and replace ingredients via the central database. But you can also privately load your own database. Nobody else will see that. And of course, with both, you can privately formulate your ingredients, your formulation. And each ingredient will perform to the utmost. Some PrediMatch examples. In the database, you can filter through the ingredients that you're looking for, the type of ingredients or suppliers or whatsoever. You can then bring them to your formulation. So these are the ones that you want in your formulation. This is your lab bench, let's say. Or to select ingredients, and those are the ones to select from. And the app gives you all the calculations in order to find the best ingredient for your system. How does that work? For example, if you want to solubilize a solute, in this case, an active ingredient, Pantophina beta from Res Pharma, in order to solubilize that in a certain emollient solvent blend system. You load it to the formulation ingredients, all your emollients in select ingredients, and the app calculates what is the RAD? So if it's in or outside the sphere of your ingredient. And as mentioned, it should be below 1 inside the sphere, and the closest, the better. In this case, you can then select the best performing emollient and then solubilize your ingredient. And as you can see in this table, the further away from the center HSP of my active, the less you can solubilize. So it's very good to be targeting the right center HSP of your ingredient in order to have the highest solubilization. Yeah. You can also make ingredients, blends for solvents, for emollients in this case, even though they are non-solvents by themselves. So you can make a blend which is inside the sphere. So once you have that, you can find other matching ingredients like surfactants, additives, etc., etc. So solubilization and then formulating is a little bit different than dispersing. Dispersing should not be too close to the center, your polymer, in order to stabilize your particle, because else it will agglomerate. But also not outside the sphere, of course, but around RAD half. So that means halfway, facing your solvent system. In this case, we want to disperse a pigment, a carbon black, Printex G by Orion, with a waterborne dispersant. Again, we can map all those dispersants in Hansen space. Based upon RAD, you select then the best dispersant. And also here we have seen that indeed around half RAD, you will have the lowest concentration of dispersant needed in order to stabilize your pigment in your water-based coating. Once you have it, again, you can select other ingredients, make blends of coalescents, for example, for your binder system, etc., etc. So here's a picture of when adding your pigment, dispersant, and underneath you have your binder plus your coalescent. Yeah. So once you have that, you can then prepare your paint into your lab. So HSP, solubilization, dispersion. PrediMulsion is HLD is more about emulsions. Yeah. Applicable to also to polymers, or in this case also to monomers. As mentioned, the ESCN is required in order to start getting an insight in the HLD equation. So in this case, we selected butyl acrylate and vinyl acetate in a ratio 30-70, and the blend ESCN is then -1.7. We enter that into the app where we can calculate, okay, HLD should be below 0, something minus, not too far away from HLD 0 in order to develop my oil and water emulsion. So you can just put the sliders to where you want, and then it calculates, you need a CC of -0.2, sorry. And it can also suggest which surfactant do you need in order to emulsify that specific blend. In this case, lauryl glucoside is used in order to make this emulsion happening. We are still further developing PrediMulsion. So while PrediMatch is already launched in the market, PrediMulsion is still in the development phase. Even though, so this was an example about an ESCN blend. This example is more about to develop a CC blend in order to match to the required CC that you need. Here we are going to develop a microemulsion of squalane for a personal care product. The ESCN of squalane is 22. Filling that into the equation at room temperature, it then calculates that you need a CC of 3.7. We had a choice about bio-based surfactants, SPAN 80 and polysugarmules D6. Here are their CC numbers. So you can calculate which ratio of those two you need in order to get to the required 3.7 CC that you need to microemulsify the squalane. Once you predict that, then you go into the lab in this range in order to define the best range of surfactants, ratio between surfactants in order to make the microemulsion, in this case for squalane. Yeah. And it falls into the range of the predicted values, actually. So once you have this, then again, you can add all your other ingredients to it and adjust the ratios. Right. To conclude, with those web apps, we provide sustainable and collaborative formulation R&D. Yeah. That means you can narrow down a tenfold your formulation space for the development of coatings, inks, personal and home care products. You can find 100 times faster your matching, replacing and compatibilizing ingredients via the sustainable use of those predictive ingredient parameters, HSP and HLD, and in order to increase the performance of each single ingredient in your formulation to have the best performance and the lowest dosage of your ingredients. So everyone can join this science-based formulation movement. We call it more a movement, actually, because now we see in the market that a lot of companies are pushing in order to get science-based formulation implemented, because it will save you so much work. And you get a better understanding of your formulation design than you could ever had with, trying and see what's happening. The beauty of a licensee is that we continuously upgrade the database. We have a lot of collaborations with ingredient suppliers. And we're adding more ingredients. Formulators are pushing for more ingredients, and users, they can guide us on the ingredients they want in this database. So collaboratively, we add all those ingredients, and sustainably, we are using them in private in order to develop your formulations. Once you have developed them, then you can experimentally validate them in the lab. So that will drastically save on time, samples, and costs. All right, so this was my presentation. Thank you very much. And yeah, together we can make it happen.
Thank you very much, Sander. So thank you very much for a very interesting talk. There are a few questions. It would be nice if we can answer those very quickly, perhaps. So the first one is from the previous speaker, actually, Sébastien Guegaud, asked, what is the sensibility of the HSP and HLD measurements to the quality of the raw material?
Yeah, indeed. So we determine of the products as is, indeed. So it has a direct practical link to your lab work. So indeed, it can be, ingredients with impurities in there, et cetera, et cetera. So we don't do the calculation values because they are very precise in a pure ingredient. With the experimental determinations, we use the product as is. So we take into account all the impurities or the solvent system that it is delivered in. So with that, it has a very good link to your lab work. But yes, they are sensitive indeed to impurities, yes.
Thank you. So the other question is from Phil Jill from Raxol. And so the HSP, does the sphere size change significantly with the molecular weight and polydispersity of a polymer? This is actually related to a work I've done myself as well, where we've been trying to see if we could predict the solubility of a polymer as knowing the solubility of a monomer, because this should depend, right, on not only the molecular weight, but also the conformation, if it's in a good solvent or in a semi-good solvent.
Correct. Yes. So besides that, every ingredient has this unique center coordinate. It also has this unique sphere. And the sphere indeed can differ from a highly cross-linked polymer using the same monomers, for example. So if you have a very highly cross-linked polymer, high molecular weight, then the sphere is very narrow, a very small radius. But if the molecular weight is less, then the sphere is bigger. So that means it solubilizes better into a wider variety of solvents indeed. So that's where the difference is. And again, if you do the experimental HSP, you will get insight about the sphere as well.
But do you have any way to predict the size of the sphere depending on the molecular weight, or even if you have branched polymers, for example?
No, unfortunately not yet. No.
Okay, perhaps I can share my paper with you, so you can have a look if you find it useful.
Cool. Yes.
It was on a very simple polymer, so perhaps not very applicable. So there are a few others.
Yeah. Mm-hmm.
So there are a few other questions. One is about could this be applied to foodstuffs too? Do you have food safe ingredients in your database?
Not in my database, indeed. We also work for the food industry, but not so much actually. But yes, also there they're using ingredients, indeed, from which we can determine the HSP value. We did that also. So it's also applicable there. Yeah, also for surfactants, for example, or natural surfactants, as they call that, stuff like that. Yes, definitely applicable, both HSP and HLD, by the way. Yeah.
Then I'll try to go through as many as possible. So is it possible that questions.
Okay.
Yeah, a lot of people ask a lot of questions. So is it possible that we might be able to predict HSP parameters from molecular formulas if only the lower molecular weight materials, even if only for low molecular weight materials to begin with?
Yeah, as I mentioned, so there's a database of HSP values for building blocks as well, for polymers, indeed. So you can already calculate that. Yes, that's possible. It's not in our app, but it's in the software from Hansen himself. Yeah.
And then I think that was related to the machine learning one, using the SMILE, the SMILE, of course. Then the last question is, you mentioned the solubility parameters can be calculated, but most often are obtained experimentally. Is that correct? Do you still expect amount of work to characterize them to be a problem?
No, well, that's what I addressed here in this presentation. People see that it is a lot of work in order to do the experimental HSP or HLD determinations. But with our workflow on high throughput and building those robots for evaluating the samples, we can really speed up the characterization. So there's the HSP and HLD determinations. So that lowers actually the hurdle for people in order to get started with HSP. And then in our database, we have more and more, every month, this pile of data is growing. Yeah. So, yeah, and we can easily scale up robots. So we are ready for it. Yeah.
Okay, I think I went through all the questions. Thank you very much again for your very nice talk. Thank you